who had to cancel very near the starting date. He regrets not being here. On the other hand, I'm very happy to be here. And we're both grateful to the organizers for the opportunity to present this work. What I'm going to talk about is, if you like, it's a cartoon of Stokesian dynamics in a very special flow. And I realize I'm giving this talk in front of experts in discrete simulations, so I beg your indulgence, and I hope you find something interesting in what I say. So the idea is to carry out an analytical or quasi-analytical study of a particularly simple flow of a suspension. And the system that we're interested in was, in a sense, let's say, inspired by the numerical simulation of Singh and Knott, who simulated this shearing flow, simple shearing flow, that is shearing with rotation, of a monolayer, a dense monolayer of spheres in a viscous liquid. So that's a simple system that we'd like to focus on. And we're not going to, in fact, we have looked at the flow that involved rotational shearing. In this presentation, I'm going to look at a simpler, even simpler system involving pure straining, involving deviatoric strains without any rotation. So here's the picture of the flow. Once again, we have a monolayer. It's dense. We have flow incoming from top and bottom, outgoing left and right. No rotation on average. And the way we work the problem is we focus attention on a pair of spheres interacting through lubrication forces, because the flow is very dense, and a short-range repulsive force. And we allow these two spheres at some angle theta with respect to the principal compressive axis of the flow to have the translational and rotational degrees of freedom that are determined by force equilibrium and moment equilibrium on each of the two spheres. Okay, so there's a simple dynamics problem. Then the question is, how do they interact with their neighbors? And we assume that the interaction of the neighbors takes place as if the neighbors are moving with the average motion. So we have a pair of particles we focus our attention on that are equilibrated, interacting with one another through lubrication forces that depend upon their translation and rotation, and with their neighbors in a way that also depends upon translation and rotation. But in this instance, the average rotation is 0, and we know what the average rate of strain is. Okay, so let's see. So there are 3 parameters that are going to determine the results of the calculation. One is the area fraction that I denote by nu. The other is the average number of near contacts. Now this is different from the nearest neighbors. It's typically less than the number of nearest neighbors in 2 dimensions. And it's something that we don't know at the outset, but in earlier talks we received indication that a reasonable value is somewhere close to 3. And finally, there's the strength of the short-range repulsive force that plays a very important role in the results. Okay, so that's the story, and now I'll show you 4 or 5 transparencies that indicate the equations that provide the ingredients for the model. And I should say the goal is to, well, first we're going to be able to equilibrate pairs at an arbitrary angle theta to the flow. So we have equilibrated pairs that are every relationship with one another, and we're going to imagine that allows us to talk about a trajectory of sphere B with respect to sphere A, and we'll generate the equations for the particle separation, that is their distance, the distance between their edges, essentially. We're going to generate a differential equation for the distance between the edges and the angle of orientation. And we'll be able to indicate then how sphere B moves with respect to sphere A. And of course, we'll be focusing on the first quadrant here, but because of symmetry, the similar motion is going to be taking place in the other three quadrants. And then once we have the equation of motion of B with respect to A, we can say something about the evolution of the distribution of particles along that trajectory. The simple idea is where particles are moving more quickly, we expect fewer of them. Where the particles are moving slowly along that trajectory, we expect more particles. And that gives us the microstructure, the number of particles per unit length along the trajectory. And with that microstructure and a knowledge of the interaction force between the typical pair of particles that now has been determined, allowing the translational motion and rotational motion of the particles to be determined by equilibrium, we can calculate the stresses. And what we'll see is, by virtue of the repulsive force between the particles, not only will we have a shear stress in the particle phase, we'll have a pressure in the particle phase. And that particle pressure is due entirely to the presence of the repulsive force, which serves to break the symmetry between particle approach and particle departure. Okay, so that's the story, and now we'll have some equations. So the motion is given in terms of the separation between the edges of particle B and A, and the orientation of the line of centers of BA with respect to the vertical. I'll parameterize first with time, and then I'll change that parameterization as we move along. A is the radius of the spheres. The spheres are identical. This d hat is a unit vector along the line of centers of the pair AB, and t hat is a unit vector tangent to that vector. So we've got a component of the center of velocity, relative velocity, along the line of centers, having to do with the time rate of change of the separation between their edges. We've got a component of the relative velocity tangent to the line of centers, related to the angular acceleration of the line of centers. Now, it isn't the centers that we're really interested in terms of calculating the force between the particles. We're interested in the distance, or the motion of the relative motion of the points of near contact. So that involves the rotation of the particles, so that the omega A and omega B are the angular velocities of the particles A and B, and they provide another contribution to the relative velocity of the points of near contact. Okay, so that was for AB, and we want to determine S, and we want to determine theta as a function of time or another relevant parameter. And the interaction with the other particles, let's say the interaction between neighbor N and particle A, is the relative motion of the centers is determined entirely in terms of the rate of deformation tensor, which is going to be pure straining, and the relative velocity points of near contact is influenced by virtue of the fact that particle A does have angular velocity, but the neighbor doesn't have angular velocity because the mean shearing motion doesn't have angular velocity. Okay, so this is the motion of the points of near contact. So now let me say something about how the forces depend upon the motion. And this expression is inherited from work by Jeffrey and Onishi and Jeffrey. It looks pretty complicated, so let's see. So we've got a second-rank tensor K that operates on the relative velocity of the centers, and that tensor, let's say, of viscous force indicates to us that the component of the viscous resistance along the line of centers is inversely proportional to the separation between the edges. Okay, that's the lubrication force. The tangential component is not so strong. It goes like the logarithm of the inverse of the separation. So that's a contribution of the force that's related to the relative velocity of the centers. Here's our repulsive force. It's assumed to be 1 over S itself, 1 over the separation. And then there are additional components. So this is related to the average motion. This is related to the rotation of A. This is related to the rotation of B. I say, and there are coefficients in there that we retain because we want to retain all contributions to the force of the same order. Okay, so that's for the pair AB. For the pairs NA, we have only the average motion, the average rate of deformation tensor. Here's a contribution. Here's a contribution due to the rotation of A, and here's the corresponding tensor K for the average motion, and this S bar is the average separation in the mixture. Okay, so that's a consistent with our idea of treating the neighbors of A other than B in an average way. Okay, so we have now the forces of interaction. And having those forces, we can calculate force equilibrium. So we calculate force equilibrium on, this is for particle A, and that involves the force that B exerts upon A, and also the forces that the neighbors N exert on A, where we assume that there are capital N superscript A neighbors of A, and this is meant to exclude the presence of particle B. And we can write a similar force balance for particle B, taking into account the forces equal and opposite, and we have these kinds of relationships between the unit vectors from the center of one to the center of the other. And then, for example, having done that, we take the difference in the force balance, and we see that an equation of motion, or equation that determines, or that may serve to determine the particle separation, is beginning to emerge. So here we have the time rate of the particle separation being related to the repulsive force, and quantities that I denote here by tensors. Here's a third-rank tensor and a fourth-rank tensor that are related to the way that the neighbors are distributed around A or around B. So I'll say something more about characterizing the way that the geometry of the neighbors influences this equation of evolution for the separation. So that's one of the differential equations of our interest. If we look at the tangential component of the difference in the force balances, we get a similar analogous equation for the time rate of change of the angle, the orientation angle, and that is phrased in terms of the average motion the tensor J, again, that appears here, and it also involves the sum of the angular velocities of A and B. So we'd like to be able to relate the sum of the angular velocities to the time derivative of theta and the time derivative of the separation if we can, and the moment balances provide us with the means to do that. So in the same way we calculated the force balances for the two particles, we can calculate the moment balances using a two-dimensional alternating here or antisymmetric tensor. And let's see, and the sum of the momentum balances then provides us with the relationship between S and quantities that appeared in the earlier equation. It introduces a new tensor characterizing the distribution of the neighbors about the particles A and B. Okay, so now I've got to say something about this. I've got to make some characterizations about A, J, and Y. And the first thing we say, well, now we're getting crude. The first thing we say is that all pairs of particles with the same orientation, either in one direction or let's say along the same line, plus or minus, they all have the same neighbors. This is a gross assumption, but we'll make it. It's relatively transparent. So at each orientation, we're only focusing on a typical pair of particles, and we're assuming, in addition, that the neighborhood of B is the same as the neighborhood of A. And if we make that assumption, then we can begin to get some definite representations for these tensors. Okay? And I'm going to make an even broader assumption. I'm going to say that I'm going to derive these representations assuming that the neighbors are in a situation that is isotropic. And of course the question is, why wouldn't it be isotropic? And the answer is because we have the shear rate tensor also in the problem. But I'm going to ignore that, although I'll show you its influence a little bit later. I'm going to assume that these neighboring particles are distributed as if the average shear rate wasn't present. And if that's the case, then the average of this sum, which is the sum calculated knowing that particle A is in contact with particle B, let's say, this sum only has one direction, and that's the direction of the unit vector along the line of centers. So this is an isotropic representation of this vector characterizing this combination of neighboring unit vectors. There's an analogous second-rank tensor characterizing this tensor product of neighboring unit vectors, and that has an isotropic representation in terms of this unit vector, in terms of two parameters. And finally, the third-rank tensor is the isotropic representation of this summation, and that involves two additional parameters. Okay, so I can use these relations. In the equations of motion that I have, but it wouldn't be beneficial if I didn't have some way of relating these coefficients to more fundamental quantities in the problem. So now let's carry out explicitly some averages. So before I do that, I should say the way I'm going to characterize the average separation between the particles is in terms of a relationship from two-dimensional statistical dynamics or mechanics of disks. So this is an appropriate expression for a colliding gas of disks, equilibrated, not sheared. And the radial distribution function at contact that I'm going to use is that determined in numerical simulations by Verlet and Levesque. So I'm going to relate the average separation of the edges of the neighbors to the area fraction. So that's fine. So I've eliminated, or I've related at least, the average separation to one of the variables in the problem. And then I'm going to calculate the coefficients that appear in the isotropic representations by introducing a simple distribution function that says there's no possible neighbor that can be in the place where sphere B is, and then all the remaining neighbors have to be continuously distributed over the space available in such a way that the distribution, using this distribution, we calculate the appropriate number of average contacts per sphere. So K is sometimes it's called the coordination number. So K is a coordination number. That's one of the parameters that I said we were going to have to specify in order to close the problem. And what we're able to do by carrying out this averaging for each of our tensors is to relate the coefficients that appeared in their isotropic representation to a single parameter. And that parameter, alpha, depends upon the coordination number. Okay, so now we've assembled all the ingredients that we need to formulate a set of evolution equations for the particle separation and the particle orientation. We'll introduce explicitly now the pure straining motion. Gamma dot is the shear rate, and what results is a pair of evolution equations for the particles separation and the particle orientation. These still involve the sum of the angular velocities, but if we combine the tangential force difference with the sum of the moments, we obtain a relationship between the sum of the angular velocities and the angle itself. So we'd like to solve these differential equations in order to determine what we regard as a representative trajectory for the motion. Of course, we have to be careful of what we mean by that representative trajectory. And what we mean is that we want to capture, let's say, the average motion of those particle trajectories that are important in determining the stress. So these are typically, the most important trajectories are, I would say, a bundle of trajectories near the surface, at and near the surface of sphere A, over which that contributes significantly to the calculation of the stress. And in the numerical simulations, in the Stokesian simulations, typically is identified a range of the radial distribution function over which the stress is calculated. So what I call a typical trajectory then is a representative trajectory for, let's say, a bundle of trajectories in that interval about the edge. Okay, now let me say something about the number of contacts along the trajectory. So this quantity A of theta is the number of contacts within an interval d theta. And because this is the trajectory now consists of particles that are in equilibrium, trajectories can't join one another or depart from one another. So there's our representative trajectory is a single trajectory along which the flux of particles is conserved, so that the way that the distribution of particles is determined is by requiring that the product of the distribution and the angular velocity. Now here I'm parameterizing in terms of the total strain. rather than the time. The time can be factored out of the problem. A is determined by this product being equal to a constant, and that constant then is itself determined by the fact that the integral of the distribution over all angles is equal to the average number of particles per sphere. And if we focus our attention only on the upper quadrant, it's the coordination number divided by 4. And we implement this as differential equations just because that's the easiest way to introduce this integral constraint that determines the constant. So we introduce two differential equations, one based upon this partial integration of A, and that allows us to determine or to implement the integral condition as boundary conditions for this pair. Okay, so that's a little technical. So here's a set of differential equations we're dealing with. So I started out parameterizing by time, then I moved to parameterizing by total strain. Now I'm going to parameterize by theta. So we have separation, the evolution equation for separation. It's known, right-hand side is known as separation, orientation, and parameters. We have a similar evolution equation for distribution. Here's this the partial integral related to the distribution itself. And the reason I eliminated gamma as the independent variable is I want to introduce it as a dependent variable because I want to further constrain the trajectory to be completed in the total amount of strain that it takes an average trajectory to be completed. Okay, I need constraints on the trajectory in order to come as close as I can to determine it without introducing more information from the outside. So this is my set of equations. I've got 4 equations parameterized by theta. And I introduce boundary conditions on the starting separation and the final separation. And these are seemingly arbitrary. The question is why choose these particular numbers? And it's because these particular numbers yield trajectories that have average separations that are near average separations seen in the Stokesian dynamics simulation. So if you like, here we're taking more information from outside the calculation into the calculation. So that's the explanation of these boundary conditions. We have the coordination number K entering here, and finally our estimate of the total strain necessary to complete a particle interaction is here. So it's a set of differential equations. It's not particularly difficult to integrate them. There's a solver in MATLAB called BVP4C. You can integrate them easily, and I'll show you the results then of the integration. So here's a figure that shows the particle separation for 3 values of area fraction. We've taken the coordination number to be 3, that is the average number of near contacts per sphere is 3. Gamma, as I said, is 1.1. The dimensionless version of the interaction force is 10 to the 4. I think this is exactly what Singh and Knott employed. And what we see then are trajectories. Notice this is 3 times 10 to the minus 3. Trajectories at 3 different area fractions with the trajectory corresponding to the greatest area fraction being the closest. These trajectories exhibit asymmetry about pi over 4. because of the presence of the repulsive force. Now, in order to emphasize that asymmetry, on the next transparency, or next slide, I'll show the inverse of the separation. So showing the inverse of the separation, you see the progressive development of asymmetry with the increase in volume fraction. That is, that the lowest volume fraction it's difficult to see asymmetry, but as the area fraction increases, it develops. I'll show you the angular velocities of the three trajectories simply because it's the angular velocity that serves to determine the distribution function. And now I'll show you the distribution function for two values of the repulsive force, 0 and 10 to the minus 4. So this is the trajectory that you would get if the repulsive force were absent. It's, well, two things to note about it. One is that it itself is very anisotropic. That is, isotropy would be a straight line at about 1/2 here. So there is definitely anisotropy induced in the distribution of particles by the average straining. But, so now I've shifted, in order to see the anisotropy, I've shifted distribution function up by 10. But the presence of the repulsive force introduces an additional anisotropy that is asymmetric about pi over 4. And this is the asymmetry that is reflecting the fact that the repulsive force breaks the symmetry between approach and departure. So here's sketches of circumferential distribution, that is A at various values of the area fraction. It becomes more and more anisotropic, that is the particles will spend more and more time along or in the neighborhood of the principal compressive axis. And in addition, the interval changes slightly. So that's distribution. As I said, distribution allows us to calculate the stress by taking the integral over the contact force. We can determine the contact force in terms of average properties, and we'll make things dimensionless in order to clean things up a little bit. So the relationship between the motion and the stress, so here we've normalized by the rate of shear, is given by this formula. Everything is explicit in this formula. That is, we can carry it out. We can carry out the integrations numerically because we have at our disposal the quantities that appear here. I'll do that. And we have an expression then for the pressure that involves not only explicitly this repulsive force, but also a distribution that is anisotropic. If the repulsive force were not present, as we saw, this distribution would be symmetric about pi over 4, and this integral, in the absence of f here, would vanish. So the anisotropy of A is a crucial component in the determination of the pressure. In fact, this is making an insignificant direct contribution. Its importance is in determining the anisotropy of the distribution. And the anisotropy of the distribution influences the shear stress, but doesn't determine its existence. So here are the quantities, let's say the magnitudes of the shear stress and the pressure given as functions of area fraction for this situation that we've looked at. So once again, it's the asymmetry about pi over 4 that creates particle pressure. Oh, and I'll just take 1 minute. So the question is, given this analysis, what's the tensorial structure of the stress? And I'll answer that question with this relationship here. That is the tensor, the relationship between the stress tensor and the stretching, given here in dimensionless terms, has a very small contribution from this second moment of the distribution, and the dominant contribution from the fourth moment of the distribution. Okay? Let's forget about that. So here are my conclusions, and thanks for your attention.
From statistical mechanics, a couple of expressions from kinetic theory. One having with dependence on nu, the area fraction.
The average area fraction.
Yeah.
Yes.
And then the question, and I didn't see how that ultimately came into the picture, but the question is there some relation between that and the force of repulsion that you assume between the particles? Is there some redundancy here, or?
Well, so the neighbors, the force between, let's say, particle A or particle B and their neighbors depends upon that average separation, while the force between A and B depends upon the separation that we determine as part of this evolution.
Well, and so you consider those things to be completely different and distinct,
yes,
independent. I think that's
yeah.
Go ahead.
I have two questions. One is, so when you say that particles A and B have the same neighborhood, does that mean the number of particles around A and number of particles around B are the same?
On average, yes.
On an average.
Yeah.
Other one is the repulsive force, you take it to be 1 over S. The repulsion between the particles is 1 over the reciprocal of the separation distance. It's proportional to?
The normal component is 1 over the separation of the edges. The tangential is the logarithm of that.
Okay. So what is the justification for taking 1 over the separation distance?
Pardon me?
What is the justification for taking this 1 over S?
That's the interaction force that's appropriate for viscous interaction between particles in a slow flow. That's the calculation of Jeffreys and Onishi's that we made use of. I mean, that was not a calculation we did ourselves.
Okay. Over here. No? Somebody else? No, please go. Go ahead. I'll ask you later.
Thanks. I have a question about the fourth order term. First, a comment. In experiments recently, we've seen fourfold symmetries in the shear thicken state being subtle but an important part of the structural component. They're not naturally arising in a suspension under flow. And I believe some of the people in the room have simulated things that have shown similar fourfold symmetries arising when you have friction, maybe, right? You've seen also. But I'm wondering, it seems requires that it's not just lubrication, but you have to have that short range repulsion for that fourfold symmetric term to be an important part of the stress
Yes.
tensor? Okay. So that's
Yes.
highly
I
dependent
mean,
on short range.
yes, without that, the distribution function would not have the asymmetry for that term to contribute in the way that it does.
So in this model, seeing evidence of that fourfold symmetry would be a signature of having a short-range repulsive interaction in the system.
I would think so, yeah.
Thank you.
Okay, last question.
So I'm just wondering, why is this analysis restricted just to a two-dimensional flow? Because the resistivities are taken to be from a 3D problem. So is that...
Yeah, so the idea is that the spheres are totally immersed in a three-dimensional fluid, but residing on in a two-dimensional plane.
So I'm saying, is that because one has to solve for the separation as a function of only one angle instead of the other meridional angle if you do it?
Yeah, so exactly, the problem is simplified to deal with only one angle. I mean, we can generalize the calculation to 3 dimensions, but that's just a complication, really.
Okay, can we end this session by first thanking Jim for this talk?
Yep.